Hello, and welcome back to the Taurus Report, where we are the bull in the China shop of cosmology. And what that means, I suppose, is that as we go on, we're going to be breaking some things. But before we break things, we want to see how it is that the China shop got built. How did standard cosmology get built into the edifice that it is? And it was built over the course of decades by thousands of the most brilliant scientists we have. And so it is no small project to criticize it and to propose something different. But before we can criticize it, we need to demonstrate an understanding of it so that later our criticisms will make sense. And central to that project is going to be understanding what the CMB is all about, the cosmic microwave background radiation. As we discussed in our previous episode, standard cosmology interprets it as the relic of the Big Bang. In other words, it's sort of an afterglow that we're seeing from the Big Bang. In our previous episode, I explained how cyclic cosmology, cyclic gravity and cosmology doesn't explain it that way. Cyclic gravity and cosmology explains it as light that leaves the central universe, and it hits a portion of the galactic, intergalactic medium that's beyond where all of the galaxies are, and then through Compton scattering, the light is changed and then comes back to us. And so we're seeing sort of, according to cyclic gravity and cosmology, we're sort of seeing a reflection of ourselves many billions of years later. And so those are two very different interpretations of what the CMB represents. So what I would like to do in this episode is to explain why the CMB is so important to standard cosmology, which is called GR LCDM. GR is general relativity. LCDM is Lambda Cold Dark Matter, where the lambda represents the rate at which the universe is expanding. So let us take a look at the CMB and see why it is so important to standard cosmology. When Hubble looked out into space and he observed that most galaxies are accelerating away from each other, that created an immediate problem. Wherever you have an acceleration, that means that there's some kind of force acting. And I need to be a little clear about something because it might not be that clear to a typical layman. When we say galaxies are accelerating away from each other, it's not like an explosion. Like sometimes people think that the Big Bang is like some kind of explosion. And so if we think that the Big Bang was an explosion and we look at it like that, then it sort of might make sense to think that, okay, so galaxies, dust and gas are expanding away from each other and they form, the dust and gas will then form different galaxies and so on and so forth. And that isn't what we're really meaning by the Big Bang and cosmological expansion. For one thing, when you have an explosion, of course, at the beginning, you expect things to be moving away from each other. Like, let's say you have some object, with at the heart of it, there's some dynamite or something, and you blow that object up, okay? And let's say you're watching it, you have a camera and you're watching it in slow motion, okay? At the beginning of the explosion, when the gases are expanding, little shrapnel and bits of the object that have broken apart, they might accelerate for a short time as the gas is expanding. But after it gets out of the radius where expanding gases are accelerating it. Okay? Once it gets out of that radius, then from then on, you would expect that the velocity of the shrapnel would hold steady, sort of like a bullet. If you shoot a bullet from a gun, of course, inside the gun, you expect that that bullet is going to be accelerating, right? But once the bullet gets past the muzzle of the gun, as the bullet travels through the air, it's traveling at a very fast velocity, but you expect, because of air friction and whatever, over time, that bullet's going to lose energy, and over time the bullet will slow down, right? So for a while it'll travel at what seems like a pretty constant speed, and then after a while the bullet's going to lose energy and slow down. And so in an explosion, that's what we kind of expect. There might be acceleration like right at the beginning, okay, where the gases are expanding. But once you get beyond the expanding gases, you expect everything to travel at a constant velocity, and then even after a while to kind of slow down. Here on Earth, things would slow down because of air friction, or they might slow down because gravity pulls them to the Earth and then they hit the ground and start rolling or whatever, okay? But we don't expect the explosion to just keep going, right? Now, when we're thinking about in terms of the universe, sort of similar reasoning, okay? If there was some kind of explosion at the beginning of the universe, if that's the kind of thing we're talking about with a Big Bang, then what we'd expect is, expanding gases at the beginning, so objects would be accelerating away from the center because of the explosion. But once they get beyond a certain radius, we'd expect them to travel at more of a steady velocity, right? Steady velocity. And then after a while, they're going to slow down because of gravity, right? So we would expect, as we look out in the universe and we see, it would not be too surprising, what was not that surprising, if you're believing in Big Bang cosmology, it was not that surprising that we saw galaxies moving away from each other. Because if you're thinking like Big Bang, okay, so it's an explosion and they're moving away from each other, that's not that surprising, okay, if you saw that. But that isn't what we saw. What we saw instead is that the galaxies are not just moving away from each other, but they're accelerating. Okay, now that is weird. That's a weird thing to see. It's sort of like if you saw some kind of explosion and you put it in slow motion. So here's the explosion, then things are moving away from each other, then it gets out to here, and then suddenly the things, instead of slowing down because of air friction, they start accelerating, okay, and they're moving at an even faster rate. So they're not just moving away from each other, they're moving away and accelerating faster. So that is unexpected. Okay, so that's weird. Now, standard cosmology will deal with that issue by appealing to Einstein's stretching of space. His general relativity posits that space can be deformed and stretched. And so instead of treating the Big Bang as some kind of explosion, standard theory states that space itself is expanding. And so the reason why galaxies seem to be accelerating away from each other is that space itself is expanding. Okay? And so that is one thing that when Hubble saw that motion, that kind of motion had to be explained. Okay? Now, standard cosmology then assumes that a lot of energy must be introduced into the universe, and I want to explain about that next. So here I've drawn a cliff with a rock at the top, and you can imagine if if this rock falls off the cliff, it's going to have a certain impact. How big the impact is sort of depends how high the cliff is. If we're going to ignore air resistance, so let's pretend there's no air resistance, like this cliff is on the moon or something, right? So that means the higher the cliff is, the greater the impact's going to be. And this is gravitational potential energy. As something gets higher and higher, of course, you're kind of storing more and more energy, however high it is. It's the same principle if you have, some river going downhill and you have some sort of like water wheel there, like a water wheel to grind wheat or whatever, or a dam generating hydroelectricity. The point is, when stuff runs downhill, you can harness that energy, and that is gravitational potential energy. Now, it's the same sort of thing if you're talking about galaxies moving away from each other. Okay, now normally because of gravity, like let's say I have two galaxies, spiral galaxies, they're close to each other, right? Now gravity would attract them. If you move them farther away from each other, right, that takes energy to do that. It takes energy to force two things that are gravitationally attracted to each other. It takes energy to force them farther away. And the further away you force them from each other, the more gravitational potential energy there is. It's sort of like with our cliff and rock example. If I take the rock and move it up to this small cliff, right, that takes energy against gravity to put that rock up there. Now, if I go even further up an even higher cliff, it takes more energy. So the further away that this rock is from the surface, the more gravitational energy is being stored. And likewise, and that applies for any objects that are moved away from each other, right? There is gravitational potential energy being stored. Think of it like a spring, if you're stretching a spring, because there's an attraction, a gravitational attraction between these two things, in this case, the Earth and the rock. Or over here, between two galaxies, there's a gravitational attraction, and if you're forcing them apart, it's sort of like you're stretching the spring, okay? And so the energy that is being created in order to stretch these things apart, that is what we call dark energy. And because most gravities are expanding away from each other, this dark energy is most of the mass/energy in the universe. So it was Einstein with his famous equation E equals mc squared. Basically, he's saying that energy and mass are two forms of the same thing. And so when we look out into the universe and we see galaxies like accelerating away from each other, this is interpreted by standard cosmology as energy being inserted into the system, that there is some energy being inserted into the system. And when they do calculations, under this interpretation, which I happen to disagree with, by the way, but we just want to, as I said with the bull in the China shop comments earlier, first we must understand how the China shop got built before we start criticizing it and causing things to break. But in any case, so standard cosmology interprets this as a constant stream of some form of energy being inserted into the universe. And that is what they're calling dark energy. And it is necessary because if these things have gravitational attraction, you need energy to accelerate them away from each other. And I promise we will get to what this all means as far as the CMB and why the CMB is important. We will be getting to that. There's another thing that astrophysicists saw looking out into the universe, something also very unusual, hard to explain. We just talked about how it's hard to explain why galaxies would be accelerating away from each other. But there's another thing they saw. So if you have some spiral galaxy here, okay, and I'm going to try and So there's our spiral galaxy, a little schematic of a spiral galaxy. When they looked at various galaxies, looking out into the universe, and they looked at stars on the edges of galaxies, they found that those stars were moving too fast in their rotation around the center of the galaxy. And this is the case for nearly all galaxies that we observed. These stars are moving too fast. And what do I mean by too fast? What I mean is that moving at that speed, they should not be held in orbit. The gravitational force of the central galaxy should not be strong enough to hold these stars in their orbit. Instead, at that speed, those stars should be flying off into space on a tangent. And they're not. Now, how do they know that the central galaxy is not strong enough? How do they know that? Because we have ways of detecting dust and gas. And I will talk a little bit more about that right now. Because ordinary dust and gas, even if it's transparent, it refracts light. In other words, light traveling through it bends. So even if we have transparent dust or gas, or dust that's out there kind of in the dark, or anything like that, we would have various ways of detecting that. And so sometimes when people hear the phrase dark matter, and I'm sort of switching subjects now. A few minutes ago I was talking about dark energy, and I explained that dark energy is the energy that we assume to be injected into the universe in order to allow galaxies to be accelerating away from each other. The energy that must be injected into the universe in order to accomplish that, that's what we're calling dark energy. Now, I'm switching gears to talk about dark matter in the context of galactic rotation. So as I said, some stars on the edges of galaxies, they're moving too fast. At that speed, they should be flying off into space because the central galaxy does not have enough visible mass, ordinary matter. It doesn't have enough to produce enough gravity to be holding those outer edge stars in place in an orbit. Instead, those stars at that speed, they should be flying off into space. And so I said that the central mass of most galaxies is just not big enough. And how do we know that? People might ask, well, couldn't there be like a lot of transparent gas, or maybe there's dark dust, or various other things that we can't detect in the sense of ordinary matter that we cannot detect? And the answer is no. We have ways of detecting all types of ordinary matter, even ordinary matter that's transparent, like a transparent gas. We have ways of detecting that because it would produce some sort of refraction, even if it's transparent. So when we use the phrase dark matter, we are not talking about ordinary matter as we understand it. That we just are unable to see. That's not at all what we're talking about. When the phrase dark matter is used, it means a special type of matter which we have never experienced and we have never detected. It is matter that has mass but does not interact with light at all. It does not interact electromagnetically. And all matter that we know of does do that. Okay, so this would be a new type of matter, as I said, which we've never detected and are unable to detect any, but which standard cosmology assumes is at the center of most galaxies because we need more mass in a galaxy to be able to produce the gravity to explain why the stars can stay in orbit at that speed. For example, our own Milky Way galaxy, standard cosmologists who reason according to standard theory would say that our galaxy must have about 90% dark matter, even though we can't detect it, because the stars at the edge of our galaxy are moving that fast. It would require that 90% of the mass of our galaxy is not detectable. Okay? And that is the type of matter when we use the phrase dark matter. And now that I've sort of done this long digression, sort of explaining various accelerations that we see out in the universe that are difficult to explain, mysterious to explain. There's some mystery about them, and standard cosmology comes up with dark energy and dark matter to deal with those things. And now it is time to finally explain, like, what does all this have to do with the CMB? Now, what does all of this have to do with the CMB? Now we're ready to finally kind of take a look at that. Okay, so let's look at the cosmic microwave background radiation. We'll type that into Google here. And let's just see what comes up. Okay, I like Wikipedia. Let's take a look at that. All right, so Wikipedia. So if we take a look at a picture of it, and let's see, they must have some neat picture of the cosmic microwave background radiation. So there it is. And so it is a type of electromagnetic radiation, a type of light that comes at us from all directions of the universe. It doesn't matter which direction we look. We have this radiation, this form of light coming from us. It's in the far infrared. It's not visible to our eyes, but our radio telescopes and so forth can detect it. And so what is this difference? We see little red zones and, yellow and green and blue zones and dark blue zones. And it is just slight temperature differences in this radiation. So the different colors are just slightly different temperatures. Now, these differences are super slight, super tiny. And so the picture here is a little deceptive in that someone might get the wrong impression that there's this huge difference. But the sensitivity of the picture is such that it sort of is deliberately designed to make the slight differences really stand out. So if we saw something like this with our naked eye, it would be like totally smooth with no difference at all. Okay, so these differences are very slight. Now, since standard cosmology interprets this as a picture of the universe, at the time of the Big Bang, let's say, the slight differences in temperature are caused by differences in where matter is at that moment in time. If we think of this as sort of a snapshot of the Big Bang. And so all these differences would be, differences in the distribution of matter. And so over time, this is sort of looking back in the past. Over time, these differences would lead to the formation of clusters and groups of gas, and later the formation of galaxies, and later the formation of stars, and all of that structure where the gas goes from this, then becomes part of like big clusters of gas, and then those clusters of gas will differentiate into clumps that become galaxies, and the galaxies will differentiate into clumps that become individual stars, and so forth. And so this picture of the CMB is sort of like a kind of a snapshot of the early universe and the clumpiness. I'm going to call it clumpiness. You can see little clumps of matter. If we interpret these temperature differences as a picture of the clumpiness of the early universe, like how clumpy and How was the matter kind of like unevenly distributed in the early universe? So it's a picture of the clumpiness of the early universe. And we want to see how is that going to later develop into galaxies. And as I said, in cyclic gravity and cosmology, we don't quite interpret it that way. There's a sort of similarity in that both theories agree that we're seeing a picture of the universe way back in time, okay? But cyclic gravity and cosmology would say that that the universe over time gently expands and contracts. And so, yes, this may be a picture of when we were somewhat closer together. And it is a picture of clumpiness of the universe in the past, but it is not a Big Bang, in that even in this far distant time, you had galaxies, you had star systems, you had galactic clusters, you had all this structure, and it would be true that in that time, we might be seeing a phase of it when things were a lot closer together. That might be true. But it is not a picture of the Big Bang. Whereas standard cosmology, while agreeing with CGC, cyclic gravity and cosmology, while agreeing with CGC that this is a picture of things from the past, in standard cosmology, it is that portion of the past called the Big Bang. So for standard cosmology, that picture, the CMB, as I said, it represents the sort of clumpiness of the universe right at the Big Bang. And what we're seeing in the CMB is the afterglow of the Big Bang. Now, a fancy name for that sort of clumpiness, or the way matter was sort of distributed back then, is called anisotropies of the CMB. And there is a very formal mathematical way of describing the degree of clumpiness, and that is called the power spectrum. And the power spectrum of the CMB is something that is often referred to by standard cosmologists when criticizing any other proposed theory. They always tend to refer back to this power spectrum of the CMB and claim that any other proposed theory other than GR-LCDM, any other proposed theory can't explain that power spectrum, whereas GR-LCDM can. And therefore, I feel that they are prematurely dismissive of any other idea. And so I would like to take a look at this power spectrum and explain a little bit about it, and explain the response that I give to it from the perspective of CGC. So the power spectrum of the CMB is about clumps. And let's say you take a picture of this paper, and we got clumps of stuff that are this big, okay? And we count all of the clumps that are this big, and let's say I get like there are 7 clumps that are this big. What are these, like an inch? Let's say they're about 3/4 of an inch. So let's say I've got 7 clumps, or however many this is, like 10, 12 clumps. So like 12 clumps that are 3/4 inch, right? Then I pick a different size of clumps. Like let's say I do some different size. Like let's say I want to talk about 2-inch clumps of matter. Like how many 2-inch clumps of matter do I have? And let's suppose I've got 5 clumps that are 2-inch clumps. Okay, and we can just keep going on and on. Let's suppose I want like 5-inch clumps. So those are really big clumps. And I'd say I've got, 2 clumps that are like 5-inch in diameter. Okay? And so the power spectrum really is about that. It's just counting clumps of different sizes. That's what it is. So now going back to our Wikipedia article, I can scroll up a little bit and show you a graph of a power spectrum. They have that here. Let's click on this. Okay. So this graph, which looks exceedingly complicated, but actually is not that complicated in its interpretation. It's very complicated to make. In maybe a technical interpretation, this would be very complicated. But a rough, kind of overly simplified explanation is actually not that complicated, okay? So basically, on the left of this graph, like say you take a picture of the CMB, just like I was talking about taking a picture of my paper a few minutes ago. On the left, on this horizontal axis here, okay, you can think of it as the size of the clumps, where the left-hand side is really big clumps, like in my example that I used, 5-inch diameter clumps. So on the left side is like really big clumps, and then at the right side is very small clumps. So if we're looking back at our CMB here, okay, so like let's say we've got a big clump of matter over here, we've got like another big clump here, we've got like another big clump there. Those would be like the big clumps I'm talking about, okay? Whereas if I look at one little spot right here, this would be like a small clump of stuff. And so the power spectrum is really kind of measuring clumpiness, is a sort of an oversimplified way of interpreting it. Let's see, where is my, there it is. Okay, there it is. All right, so anyways, this power spectrum shows a peak right here, and that means that clumps of this size right here, there's a lot of them. So on the vertical axis, it's sort of like a count of how many clumps that size do you have. Okay, and then down in here we don't have so many of this size, but then we've got another peak here, and we've got another peak here, and we've got another peak here, and so forth. So we have clumps of various sizes, and how often do they occur? And we see that there's definitely a pattern here in that certain sizes of clumps are more common than other sizes. And so we're assuming that certain clumps would create galaxy clusters, other clumps would create galaxies, and if we go really far down to microscopic ones, we'd get like individual suns, and so forth and so on. And so that is the power spectrum of the CMB that everybody's often talking about if they want to shoot down other proposals or other theories. Now, the next portion I'm going to go into explaining why is this presenting like a big challenge to any sort of modified gravity approach. Why does this cause a problem for modified gravity? Now to explain finally what all this has to do with modeling, why the CMB, and responding to interpretation of the CMB, why that is so important, if one is going to propose a different theory of gravity and claim that that is what the universe operates on. So, what theorists do, standard cosmologists do, is they say, okay, here you have a picture of the Big Bang, and we are going to assume that the anisotropies of the CMB, which is looking at the CMB, if we assume it's the afterglow of the Big Bang, then the clumpiness of the CMB, if we build computer models that fast forward that over time, then our computer models should be able to predict the clumpiness of visible galaxy distribution right now. In other words, the distribution of matter in our present universe, if you have the operation of physical laws correct, if you've got that correct, then you should be able to predict from the clumpiness of the CMB, you should be able to predict the clumpiness from the clumpiness in our present universe when you look at galaxies now. So to illustrate what I mean, I want to show you an animation I found at the University of Chicago by Dr. Hu that he has publicly available on the internet. And so I want to show you that to kind of illustrate what I mean here. And I will share this link, as I've stated before. I'll share all the links in the comments, the YouTube comments of my YouTube videos. You'll also be able to get to them by clicking on the link at taurusreport.com. So here we have basically on this site, what you can do is see what happens if you and baryons is ordinary matter, by the way. So if you change the percentage of ordinary matter, baryonic matter, for cosmologists, baryonic matter means ordinary matter. Basically, it means not dark matter. Okay? Then computer models would then predict what the power spectrum of the CMB would look like. Okay? Now, as I stated earlier, the power spectrum, the way it looks in actuality right now, is this. This is what we observe on the CMB right now, the power spectrum of the CMB. And what would that power spectrum look, according to computer modelings, if we play around with the percentage of ordinary matter in the universe? Okay? And so the percentage of ordinary matter in the universe, dark matter versus ordinary matter, right? Then here is if we play around with total matter, okay, dark and total, and ordinary matter. Okay, now here is if we play around with dark energy. Right? So this is playing around with the expansion rate. And so here, if we change the fraction of ordinary matter, we change it compared with how much is ordinary matter and how much is dark matter. Okay, so as you play with these different things, then the power spectrum that you would see based on modeling the universe, like basically modeling the development of universe over time, and then sort of projecting backward and predicting what is the power spectrum you'd see if the universal laws and the ingredients of the universe, like how much dark matter, how much dark energy, how much, how things would change over time, the power spectrum would look different. Okay, the power spectrum would look different. And so that is the idea. So just to recap that, okay, so cosmologists would make a model based on the present clumpiness of matter, the present distribution of matter in the universe right now as we see it. And then they put, the proposed ingredients, like how much dark matter, how much dark energy is entering, the rate at which dark energy is entering the universe, so that would be the expansion rate. So they play around with those things and then assume that the universe developed according to those assumptions. Then they will project back and see what would the power spectrum look like under those assumptions. And then what they get is, by playing around with that, is they find that most of the universe must be dark energy. Of the matter in the universe, most of the matter in the universe would have to be approximately like 80% dark matter and maybe, 16 to 20% ordinary matter that we are used to interacting with. But just to make clear, dark energy swamps all of that out. So dark energy is the preponderance of what our universe is made of. Now, when it comes to modeling these things, there's several difficulties here. First, this type of extensive modeling is very difficult to do. I have done it to some extent, and in later episodes I will share the modeling that I have done and show you animations that show the development of a solar system using CGC. But here we're talking about models where we're kind of modeling back the entire universe, trying to model it from current distribution of matter to distribution of matter that sort of matches the anisotropies of the CMB, which is looking very far in the past, billions of years in the past, and that takes some extensive modeling. So is there anything out there that demonstrates that a model similar to CGC might result in, if you extrapolate it back, might result in seeing the clumpiness that we see in the CMB? Is there something that exists like that? And there is. Now, there's another difficulty in that, again, there's a disagreement between standard cosmology and CGC about what we're looking at when we see the CMB. Standard cosmology says that's the afterglow of the Big Bang. CGC says, well, no, it is looking at our universe far in the past, where the universe may have been smaller, okay, but not so compressed as to be able to be referred to as something like the Big Bang, just somewhat compressed. And so it's kind of a reflection where light has traveled out to the intergalactic medium, undergone Compton scattering, and has traveled back to us. And so while standard cosmology and CGC both agree that we're kind of seeing our universe billions of years in the past, they're still very much in disagreement about what we're looking at. But the point is, they both agree that it is light coming to us from the distant path. And so I'm going to give a little bit of a spoiler here. I'm going to conclude with this, a little bit of a spoiler. This paper by Pardo, and I will put the Pardo and his colleagues, I'm sorry to those I'm not mentioning, but for brevity, I'm just going to mention Pardo and his colleagues. This paper, What is the Price of Abandoning Dark Matter? Cosmological Constraints on Alternative Gravity Theories. Now, what Pardo and Spergel attempted here is to say, okay, let's assume modified gravity. And they're being a little... they are arguing in favor of standard cosmology. Basically, what they're trying to show is how absurd of a gravity law you would have to get if you assume modified gravity and you assumed that the CMB is a snapshot of the universe in the past, still assuming Big Bang, so I'm not totally sure how perfect this is going to be, but let's take a look at it. So, and I will include this link, as I said. So if we look at Pardo's paper and just kind of skim through it, we end up with this diagram here, which basically is a gravity force law that looks just like the type of law you get with CGC. And Pardo and his colleagues are saying the way you would get such clumpiness in the power spectrum of the CMB, the way you could get it, is if you had a gravitational force law that had sometimes positive values, sometimes negative values. And here a negative gravity means repulsive gravity. Okay? So what Pardo and his colleagues are saying is that you would have to have gravity that's sometimes repulsive. And we will see as we proceed in these videos, we are going to see that CGC does produce a gravity law that looks like this. Okay, CGC does claim that the expansion we see when we look out into the universe is caused by repulsive gravity, and there are circumstances and contexts under which gravity is repulsive, and we can see it immediately in the fact that most galaxies are accelerating away from each other, and so we're observing it. Now, of course, CGC does not allow the stretching of space, so CGC would be directly contradicting general relativity. And so we will continue exploring this in our next episode. Thank you all very much for watching, and hope to see you again next week when we post the next episode of the Taurus Report. Thank you very much. Bye-bye.